No electricity, no fun. Join us to learn how this invisible force works.
Let's learn about transformers and how it works.
You will be surprised to know that there is no moving part in power transfer, yet it steps up and down 11,000 volts at extremely extra high voltage. Apart from this, the three-phase induction motor is even more surprising because it also works the same way as transformer, but just rotates. First of all, the transformer works only on AC supply and not on DC. So Mr. Faraday says that when you give supply to a wire, electromotive force will be induced in it. This force will generate a field around itself, which is called magnetic field. But in AC case, this field is bidirectional, from here to here, then the strength of the magnetic field in the wire will also increase. If it is decreasing from here to here, then the strength of the magnetic field will start decreasing again. From here, when the waveform starts going in V direction, the magnetic field will change its direction and the field strength will be exactly opposite to the positive side. If AC supply is given in such a coil, then its magnetic field will be of this type in which north and south poles will also be generated, but these poles will keep changing according to the waveform. If DC supply is given in this condition, then the magnetic field of the coil will be constant, due to which this coil will work like a strong magnet. This coil can also be called an inductor, and in DC supply, the inductor becomes short circuit because there is no frequency in it. That is why transformers do not operate on DC. If DC supply is given in the power transformer, it will generate such a strong magnetic field around itself that it will pull everything towards itself. If we bring another similar coil near this coil, then this magnetic field line will cut the other coil, due to which a force will be generated in this coil too, which is called electromotive force, in short EMF, and the other name of voltage is electric force. These magnetic field lines are called flux lines in technical language, and this process is called electromagnetic induction, through which power is transferred. So in a way, wireless power transfer is taking place, and wireless chargers have also been made using this concept. You will be surprised to know that wireless chargers send only AC supply to the phone, where there are some such small leaves in the iron core of the power transformer, and all these blades are coated with varnish. We will understand the reason behind this a little further. And after connecting all the blades together, again, impregnated paper is coated on both the sides, which acts like an insulator, and after that, both the coils are set. The coils of the transformer do not touch the core. Now we can call these coils primary and secondary winding. When we give supply to the primary winding, the flux line induced in it will provide the iron core path to reach the secondary winding, which will induce EMF in the secondary winding. Now let us assume that the total turns in the primary winding are 100, and the total turns in the secondary winding are 50. Here you should keep one thing in your mind, that the EMF induced in one turn of the primary winding will be the same amount of EMF. Will be generated in one turn of the secondary winding because the same amount of flex line coming out of this one turn will reach in one turn of the secondary winding. So now if we focus on the secondary winding, all the turns are connected in series, and the voltage we get in the secondary winding will be the total of the voltage being induced in all these turns. So the voltage, i.e. EMF, of the secondary winding will be equal to the number of turns in the secondary winding. The EMF induced in the primary winding will be equal to the number of turns in primary. There is a small difference in the EMF voltage. The voltage is applied at the terminal of the primary winding. When it reaches the winding, there is some resistance in the winding, due to which the voltage decreases a little, and as soon as the voltage decreases, we see it. It is said that so much EMF has been induced. Now let us assume that if we give 100 volts in the primary winding, then we will get only 50 volts in the secondary winding, because out of 50 turns, the capacity of all the turns is 1 volt, and everyone took 1 volt of theirs and gave 50 volts, which we get in the secondary. It means the voltage has been stepped down. In the same way, the voltage is increased by increasing the number of turns in the secondary winding. Now, for some ease, we have made an equation. Number of turn in primary upon no of turn in secondary is equal to EMF induced in primary upon EMF induced in secondary. If we go one step further, current also comes, and current is just the opposite of voltage, eddy current, which we do not need at all. Sometimes such a situation arises in water that a whirlpool is formed. Similar is the eddy current which rotates in the core. That is why the iron core is first divided into thin sheets, after which each blade is laminated. The thickness of lamination ranges from 0.25 mm to 0.50 mm. Due to this lamination, the cross-section area of the core gets reduced, and the area has an inverse relation with the resistance, due to which the resistance increases, and, that resistance is the enemy of current. So in this way, eddy current losses are reduced. The iron core in the power transformer is actually made of cold rolled green, oriented silicon steel, which reduces hysteresis losses. Hysteresis losses are induced due to the direction of the magnetic field changing repeatedly. The humming noise heard in the transformer is due to the repeated change of this magnetic field, which is called magnetostriction. Due to this magnetostriction, the core of the transformer expands and contracts, which generates a humming noise. Apart from this, there are many other losses in the transformer too, but this is the main one. There are exactly 3 windings in a transformer for 3-phase, but when we look at a practical transformer, the iron core in it is like this, for a 3-phase system in which, first of all, primary winding set. If we talk about step-up transformer, there are less turns in the primary winding and the voltage is less, and current is more, then very thick copper wires are used here. This copper wire remains completely insulated. The secondary winding is prepared over the primary winding. There is no electrical connection between the 2 windings. Power transfer occurs only through the induction process. The connection of the winding is done in 2 different connections, which is the high voltage side, which is connected in star connection. 3-phase and neutral are also available in star connection. That is why you always saw an extra wire along with the high voltage line, which is neutral. The low voltage side is connected in delta connection. It has only 3 phases.
House